3I. Atlas has just completed its closest pass around the Sun, and what happened out there doesn't match what NASA's been telling us in their updates. The timing alone is pretty wild. This thing showed up right when our Sun hit the most active part of its 11-year cycle. That's when the Sun throws out massive storms, bright flares, and waves of charged particles that spread across the whole solar system. These blasts shake Earth's magnetic field hard enough to create auroras, so imagine what a small interstellar object goes through when it flies right into the middle of all that. If 3I Atlas is just a comet from another star system, it's breaking every rule we thought we understood. And if it's something else, well, we're running out of time to figure that out, because it's headed toward Earth next. So in this video, we're walking through what actually happened during that solar flyby, how it compares to what comets are supposed to do, and why some of the strangest observations didn't make it into NASA's official reports. Because the more scientists look at this data, the less sense it makes. What 3I Atlas just did near the Sun. Okay, so this close pass is what astronomers call perihelion. It's just the fancy word for when an object reaches its shortest distance from the Sun. And normally, this is the easiest part of a comet's journey to predict. The comet heats up, ice turns into gas, dust lifts off the surface, and the whole thing gets brighter. A tail forms as the solar wind pushes all that material away. Scientists have watched this happen so many times they can usually tell you exactly what a comet's going to do before it even gets there. But 3I Atlas didn't do that at all. Instead of brightening slowly like a normal comet would, it suddenly flared with light way beyond what anyone expected. And I'm talking hundreds of times brighter in just a few days. That's not something you explain by saying the surface warmed up a little. Even the most active comets only brighten somewhere between 10 and 100 times near perihelion. That's normal. What 3I Atlas did was not normal at all. But here's the thing. The brightness wasn't the only weird part. If that had been it would already be unusual. But the object also started shifting colors in a way that goes directly against what comets are supposed to do. When astronomers first spotted 3I Atlas earlier in the year, the light coming off it was mostly red, pretty typical for dusty comets. A few weeks later, it shifted toward green. Odd, but still barely within the range of things scientists have seen before. Then, as it moved through perihelion, it changed again, this time to blue. And that's where things stop making sense. A natural comet should turn redder as it gets closer to the Sun, not bluer. As the dust cloud thickens, it absorbs more blue light, so the color shifts in the opposite direction. For 3I Atlas to go from red to green to blue means something completely unexpected is happening to the material around it. Could it be some rare gas suddenly pouring out? Maybe, but you'd need a huge amount of gas to cause such a strong shift, and nothing about the pattern matches what scientists usually see in comet chemistry. So why would an object flash blue and then change its path almost immediately afterward? Right after the blue surge, astronomers noticed that 3I Atlas was no longer moving exactly where gravity predicted it should be. Now, everything in the solar system follows paths shaped by the pull of the Sun and the planets, and scientists can calculate those paths with incredible accuracy. When something starts drifting off that path, it means another force is acting on it. Scientists call this non-gravitational acceleration. Most comets show a little of this because gas jets act like tiny thrusters. But here's where it gets weird. 3I Atlas barely showed any wobbling for months. Its path had been almost perfectly smooth the whole time, which is already unusual because comets tend to drift as they heat up. But right after that flash of blue, the object suddenly began accelerating and shifting sideways, almost like something inside it turned on. And the timing is what makes this feel so strange. Why did all three things, brightness, color, and motion, happen in the same short window? If dust caused the color change, it should have shifted slowly, not suddenly. If gas jets caused the motion, we should have seen signs of them way earlier. Instead, everything happened at once, exactly when the sun's energy was the strongest. That makes you wonder whether the sun triggered something hidden under the surface, something that reacted in a way we don't fully understand yet. Now, what does it mean when an interstellar object acts like it has its own power source? It doesn't prove anything artificial, obviously, but it does make scientists rethink what natural processes might exist in objects that didn't form here. A burst of trapped gas or a sudden collapse could cause some of these effects, but none of these ideas explain everything we've seen. The brightness jump was too strong, the color change too fast, and the path shift happened at the exact wrong moment for randomness. If something inside reacted to the sun, this mix of light, color, and motion is exactly what you'd expect, and honestly, the timing's impossible to ignore. But if this really was something waking up inside the object, then the question becomes pretty simple and pretty unsettling. What happens when it reaches us? How comets should behave, and why this one doesn't. Alright, so a normal comet's actually pretty easy to understand. At its center, it's just a big mix of ice, dust, and rock. When it gets close to the sun, that ice starts warming up and turns into gas. That gas spreads out into a glowing cloud around the comet called the coma. The coma always forms on the side facing the sun, because that's where the heat's strongest. Then the solar wind, basically a constant stream of particles blowing off the sun, pushes all the loose dust and gas away, and that creates the comet's tail. Almost every comet we've ever studied follows this same basic pattern, so scientists know pretty well what to expect when one swings toward the inner solar system. Even the little bumps and wobbles in a comet's path make sense. As gas shoots out from different parts of the surface, it acts like tiny thrusters that nudge the comet around. These pushes are small, but they do make the comet drift a little. However, even with those small nudges, a comet still mostly follows the route that gravity sets for it. Scientists can predict its movement quite accurately. That's one reason astronomers pay close attention when an object moves in a way that doesn't fit the math. Comets usually don't surprise us in big ways. They wobble a little, but the overall path stays close to what gravity tells them to do. Brightness is another thing comets handle pretty predictably. As the sun warms them up, more material escapes, and the comet gets brighter. The increase can be big, but not too big. A very active comet might brighten 10 or maybe even 100 times as it gets close to the sun, and that's still considered normal. Whatever's on the comet's surface, dust, ice, gas, all works together to create this smooth increase. But with 3I Atlas, the brightness didn't just follow the usual pattern. It shot up hundreds of times brighter in just a few days. That's the kind of jump that makes scientists stop and ask what could possibly release that much energy so suddenly. Because nothing about that fits normal behavior. So what do you do when something that looks like a comet refuses to build the type of tail every comet should have? Normally, a comet's tail forms in two parts. One part's a dust tail made of heavier particles that reflect sunlight and make that bright streak people love to photograph. The second part's a gas tail made from lighter molecules that get pushed in a straight line by the solar wind. Even though the two tails look slightly different, they always point away from the sun because the solar wind pushes everything in that direction. This is so reliable that astronomers use the direction of the tail to understand what the comet's doing. But 3I Atlas didn't do that. Instead of forming a smooth tail that stretched behind it, it produced several thin, sharp jets of gas shooting in different directions, and some of them were even pointing toward the sun, which goes directly against what solar wind pressure should allow. These weren't gentle features either. They were narrow and clear, like beams, and they stayed that way long enough to be photographed. That's not how normal comet tails behave, because the dust and gas should blend together quickly. Now, the object's rotation makes this even stranger. 3I Atlas spins once every 16 hours. If a spinning comet releases gas, that gas should smear into a blur as the comet turns. Instead, the jets hanging off this object stayed separate and crisp, almost as if something was keeping them in place. This is very hard to match with ordinary comet physics. When a comet vents gas unevenly, it usually produces messy, fuzzy shapes. Sharp jets that stay straight even while the comet rotates. That suggests something much more powerful or focused is happening on the surface. So how do you explain an object that follows comet rules in some ways, but breaks them completely in others? That's what scientists keep running into with 3I Atlas. Every time the object does something normal, like forming a coma or warming up, it immediately follows it with something that just doesn't fit. The brightness should have increased gradually, but it exploded instead. The color should have shifted toward red, but it shot toward blue. The tail should have formed clean lines pointing away from the sun, but instead, the object fired jets in several directions at once. And the rotation should have blurred those jets right away, but somehow they stayed sharp and separate. Scientists have tried using every standard explanation they have. Maybe it's releasing a rare gas, maybe the surface is cracking in unusual ways, maybe the comet has an odd shape that focuses the jets. But each explanation solves only one problem at a time, and as soon as you apply it, another part of the behavior stops making sense. And that's the main issue here. The more scientists study 3I Atlas, the less it behaves like a normal comet. Instead of settling into familiar patterns, it keeps doing things that force astronomers to rethink what's possible for an object like this. The images, the timing, the data, none of it fits cleanly into the standard models. Every attempt to classify it seems to hold together for a moment, and then one new detail breaks the whole idea again. That's why this object remains so confusing and so interesting, because every time we try to place it back inside the normal rules of comet behavior, it immediately pushes those rules aside. When every rule breaks at once, you have to wonder whether you're looking at a comet at all. And if it isn't a comet, then what exactly is heading our way? When a comet starts acting like a machine. Alright, so for most of its trip toward the sun, 3I Atlas moved in a perfectly steady line, almost as if nothing was pushing or pulling on it except gravity. And that steady motion's odd because comets usually wobble at least a little when pockets of gas burst out of their surface and act like tiny thrusters. But this one hardly moved off course at all for months. Then, right at the moment it reached its closest point to the sun, everything suddenly changed. It began speeding up and drifting sideways in a way that didn't match any of the normal predictions. The timing was so exact that scientists immediately noticed something was off. Now, non-gravitational acceleration, movement not caused by gravity, isn't rare by itself. Comets release jets of gas all the time, and those jets can nudge them in different directions. But those nudges usually build up slowly as the comet warms, not all at once in a sudden jump. What happened with 3I Atlas was completely different because the change hit right at perihelion, almost like the object waited for the hottest, most intense moment to react. The force also seemed much stronger than what a comet-sized burst of gas should create, which made the shift look less like random venting and more like a purposeful push. If the jets had been active earlier, we would have seen the comet wobble long before it reached the sun. Instead, nothing happened until everything happened at once. So why would an object stay perfectly calm for months and then suddenly move as if something fired inside it? That pattern doesn't match what scientists usually see in natural objects, because natural processes almost never line up so neatly. The brightness spike, the sudden blue color, and the sharp change in direction all happened in the same short window of time. And that window lined up perfectly with the moment when the sun was blasting out its strongest energy. When so many unusual things happen at the same moment, it becomes harder to treat them as coincidences. But okay, stick with me here because it gets even stranger. Right after perihelion, the small, sharp jets that had been sticking out of 3I Atlas suddenly reorganized into a single huge plume of gas stretching almost 3 million kilometers away from the sun. To put that into perspective, that's like taking a cloud of material and stretching it across a distance larger than 7 times the space between Earth and the Moon. Within only about a day, normal comets simply don't build structures that large that quickly. And while that plume was forming, another structure appeared on the opposite side of the object, a sun-facing anti-tail. Now, a tail pointing away from the sun is normal since the solar wind pushes everything back, but a tail pointing toward the sun, especially this close to it, that's extremely unusual. The solar wind should have blown that material away instantly. Yet it didn't. The amount of material the object lost in that short time was enormous. Yet even after throwing out millions of kilometers of gas and dust, 3I Atlas stayed completely intact. Most comets would have cracked apart under that kind of stress because their cores are usually more fragile, like loosely packed snow. But whatever's inside this object seems to be much denser or stronger than expected. The way it held together became one of the biggest surprises, because that level of activity should have torn it into pieces. This brings up another important detail: the size of 3I Atlas. Early guesses suggested the core might be a few kilometers across, but later observations made it look bigger, possibly around 10 kilometers wide. For an interstellar object, that's huge. And here's why that matters. Bigger objects are much more likely to hit dust, rocks, or even entire stars during their journey through space. That makes it very hard for something this large to survive billions of years. Yet this one did. And not only did it survive, but it arrived on a path so precise that it passed extremely close to the sun without falling in or being thrown off course. That level of precision is another reason scientists keep wondering how this object managed to stay so stable for so long. Now, I know this next part might sound a bit out there, but bear with me. If someone wanted to build an engine that used the power of a star, what kind of signs would you expect to see? You might expect sudden bursts of light. You might expect sharp color changes as different materials heat up. You might expect strong directional jets, and maybe even movement that doesn't follow the exact rules of gravity. And you might expect all of this to happen right when the object's closest to the star, where it can take in the most energy. The strange part is that 3I Atlas showed every one of those signs. Now, that doesn't prove it's artificial. It simply means the behavior overlaps with what a star-powered engine might look like. Scientists are being extremely cautious about these comparisons because unusual behavior doesn't automatically mean something intelligent is behind it. But even when they try to stick to natural explanations, the puzzle only gets more complicated. The acceleration doesn't match what normal gas jets would do. The timing looks too perfect for randomness. The giant plume and the sun-facing anti-tail appeared far too quickly for simple heating, and the strength of the core raises new questions about what the object's made of and how it survived all of this without breaking apart. Every time a natural idea is suggested, it explains one part of the behavior but not the next part. And the pattern never fully fits. So now, as 3I Atlas moves farther into the inner solar system and gets closer to Earth, the big question becomes impossible to avoid. Are we watching a strange piece of ice and rock being torn apart by the sun's energy? Or are we seeing something that behaves more like a propulsion system adjusting its course before it heads straight past Earth? Thanks for watching. If you enjoyed this, don't forget to like, comment, and subscribe. Click the next video for more exciting content.